Good afternoon. Welcome to the Nashville Public Library. I'm Susan Earle, the main library administrator, and I'm so glad you're here. I get to do the fun things like if you got something like a cell phone or anything electronic, you need to turn it off, that'd be great, okay? And here comes another wonderful piece of what I get to say, which is, and I really have seen it, so all of you should before you leave today, is our Holidays Remembered exhibit in our courtyard gallery. It'll bring lots of memories. I didn't grow up in Nashville, but it brought lots of Knoxville, Tennessee memories. So do go see it. We can't do what we do here, you know, without the Vanderbilt University as our partner, and I'm so appreciative they are. So without further ado, I would like to introduce, as usual, Christine Bradley, the Assistant Vice Chancellor, Neighborhood and Government Relations. Woo! Please give her a hand.
Welcome, welcome. I have a couple of announcements. One is the Osher Lifelong Learning materials that are on in the back. This is the time of year to sign up again for the winter term, and it's going to be a great series, so don't hesitate to take some of the pamphlets back there. The other thing is the last time we were here, it became a little bit confusing as to what to recycle and what not to recycle. I have found that our lunch boxes have already been recycled once, and unlike cats who have 9 lives, they can't be recycled again. So, you know, if your box lunches need to go in the trash. So that helps everybody. They've already been recycled once or twice, so they don't need to be, that doesn't need to happen again. Today, I just wanted to thank Dr. Wood for bringing our speaker with us today. Again, I was looking at the topic and realized that it was about the Big Bang Theory. Can we really recreate the Big Bang in a laboratory in miniature? And I thought, my God, I can sometimes not even recreate or create dinner over my oven. So this is going to be an interesting topic today, and I appreciate once again Dr. Wood for doing this and for always pulling together a fabulous speaker for us. Thanks.
Well, thank you, Susan, and thank you, Christine. We're another wonderful speaker for you today. Vicki Greene is a professor of physics at Vanderbilt, specializing in nuclear physics, and more recently she's been promoted, I don't know, executive dean in the College of Arts and Sciences, a position of considerable power and responsibility. She has a PhD from Yale, 1992. A couple of years later, she came to Vanderbilt, and she's been here ever since. As a scientist, she plays an active role in the American Physical Society and in Phoenix. In the last 10 years, she's published 182 papers in top scientific journals and has received millions of dollars in research grants from the Department of Energy. I would like to tell you more about her work, but to be honest, much of it is highly technical. Among the more accessible titles, for example, is Search for Neutral Strange Quark Matter in High-Energy Heavy Ion Collision. That's the one that I understood. I'm sorry, I shouldn't do this. Suffice it to say for the moment that Professor Greene works on the fundamental particles of which everything is made, and that physicists learn about these particles by watching what happens when they run into each other at high speed. She's going to talk to us today about experimental work in which she and her colleagues believe they can recreate the kind of particles that existed just after the Big Bang. You remember that? It was about 14 billion years ago. It's before our time. As a philosopher, I have to say I'm puzzled by the very idea of the beginning of the universe, because it's hard not to ask, what was it made from? Why then? Who made it? What for? And I'm tempted to ask whether we can or should expect answers to these kinds of questions from physics or from Professor Greene. But I'll pass it over to you.
So do I need to stay tethered here?
You want to stay there?
I can, or I can. No, it's fine.
If around and just take that with you.
Oh, okay.
I think that may just be recording, so you may need to speak there to get the sound in the room.
Oh,
See what
okay.
I'm saying?
Sure. Is that,
You can
so we have technical problems?
I don't think you need that to speak to this audience.
Oh, okay. We'll put it back then. Okay, I think we're set. Well, I just wanted to thank you for the opportunity to share my work with you. Back here hastily wrapping up these words. I'm going to talk about the early universe and a new state of matter, and I'm also going to talk about how to do physics with 400 of my closest collaborators. Now I need to get this part of the, there, okay. So here's the outline of my talk. Get here. Sorry, the response is a little slow. There, okay, I think I've wrested control back. Well, this will fit in very well with part of the theme of my talk. So here's my outline. I'm going to be talking about how you choose the recipe for your quark soup. Mise en place, getting ready, heating up the cooktop, mixing the ingredients, cooking the broth, tasting the soup and asking, is it good? So I'd first like to show you this picture of my daughter, Nora. And I think this picture personifies the wonder that a child feels when looking at the natural world. In this case, she's looking at a piece of ice that she just picked up from the ground. This is an apt photograph for this talk because most scientists are driven by the same sense of wonder throughout their lives. And I want to try to convey this to you in my talk. And the other thing is that it's apt because the ice is just starting to melt. And I'm going to tell you about a different type of melting. This is making the transition from solid to liquid. And I'm going to talk about making a melting from a state of matter that existed in the very stages of the universe, the very early stages of the universe. So first, I'm going to take you through some powers of 10 so that you know what matter is made of down to the smallest scale we know. When I was a little girl, I wanted to know what a watch was made of, so my mother gave me a jeweler's screwdriver and a broken watch and let me take it apart. And I'm not going to tell you about all the unbroken watches I took apart after that and how much trouble I got into. And I wasn't a prodigy, and none of them ever worked again. But even now, my impulse when I want to understand something is to take it into smaller and smaller pieces. This isn't the only way of knowing, but it's my way of knowing what something's made of. So think of a diamond. Unlike a watch, it's not really that obvious that the diamond is made of smaller parts. But in fact, if you look closer at a diamond on a scale of about 1/10 of a nanometer, and a nanometer is 10 to the minus 9th meters, you can see the individual atoms of carbon in the diamond lattice. If you look smaller, this is now just an artist's conception, a calculation of an atom with the electron orbitals that quantum mechanics lets us calculate. And this is on the scale of 1 nanometer. If I look even closer then, I can see the atom itself is a complex structure. It's got a tiny nucleus and an electron cloud. And most of it's empty space. If you were holding a nucleus in this room the size of a baseball, the outermost electrons around that nucleus would be somewhere out near the Parthenon. So it's a lot of empty space. So then we can see that we have inside the nucleus, which is this structure in the right, and this is 4 millionths of a nanometer. But we can go even further, looking closer and closer, and each one of those protons or neutrons, which we call nucleons so that I don't have to keep saying protons and neutrons. We see that each one of these contains 3 smaller particles called quarks, and then they're bound together by something called gluons, which are the kind of sticky particles that stick them together. Okay, so that's what we would see if we could take a diamond and look closer and closer. And that's it as far as we know, but that's as much as we know for now. So if we look at the motion of the stars in the universe, the pattern of motion points to a picture of the universe as having started at a single point. In the Big Bang, the universe expanded and cooled, and matter formed into energy. And now I have to go there. Okay, so here is a history of time, and the Big Bang comes at the very top there. The universe expanded and cooled, and as it cooled, it changed. By 10 millionths of a second after the Big Bang, the hot, dense universe consisted of quarks and gluons, just the same as we find inside one of the nucleons. And we call that a quark-gluon plasma. After 1 second, the quarks had become bound into nucleons and other particles that we find them today, which we call hadrons because they're made up of quarks. Eventually, the nucleons formed nuclei, and later the electrons were attracted to the positively charged nuclei, and neutral atoms were formed. By the time the universe had celebrated its billionth birthday, gravity was dominating and the galaxies were forming. And that's what you see down here at the bottom. And then you can see here the modern universe with our library in it and all of us. Okay, so we want to learn about these early stages of the universe, the era of the quark-gluon plasma. It's really the earliest stage that we can form an idea of what it was like. But there's a difficulty, and that's that we cannot find any free quarks to make a quark-gluon plasma out of. And the reason for this has to do with the fact that the force between the quarks is called the strong force. And it's strong because it's the strongest of the 4 fundamental forces that we know. It's the force that holds the quarks into the nucleon, and it's the force that holds the nuclei together. So if you hear about the nuclear force, this is the same force. It's very different from gravity, and it's very different from the electric force. It gets stronger. If you have 2 particles bound by this force and you pull them further apart, the force between them gets stronger and stronger. It's kind of like a rubber band that pulls further on you, harder on you, the further apart you get the ends. And the further apart the quarks get, the more energy is stored in this field between them. And at some point, there's enough energy to make 2 more particles just because mass can be transmuted into energy. And so these particles will form, and you've got a pair here and a pair here. And you never can pull one single quark out and get a free quark with which to start assembling your quark-gluon plasma. So that's the difficulty. We only find quarks bound in 2s and then 3s like the nucleons. We call these particles hadrons to distinguish them from electrons and photons are just particles of light. So they're some of the fundamental particles in the universe. However, and this is just a picture of this happening. You start with trying to pull 2 quarks apart, and the force between them gets stronger. The little colored things are the gluons. You can see that there's almost enough energy to form 2 more quarks, and eventually the bond breaks, but now you've got 2 and 2. We can actually, if the quarks are close together, the force between them is weak, and this is called asymptotic freedom, for which Gross, Wilczek, and Politzer were awarded the Nobel Prize in Physics in 2004. And this is just a picture of Wilczek's Nobel Prize certificate, which is actually very lovely, and each one is individual. So if you could get a lot of quarks close together, they would become unbound, and then we could study the system of them. Because remember, this is like a rubber band, and if 2 things tied together by a rubber band are close together, the rubber band doesn't do anything. And so that's the idea behind the experiment that I want to do, or that I wanted to do 10 years ago when I started doing it. So we start with a normal nucleus, and that's really easy to get. And then we see, okay, there are no viruses on the library's computer, so that should be reassuring. Okay, so we can start with a normal nucleus. And here you see the nucleons with the quarks and the gluons inside, and now this is familiar to you. But if we could heat or compress the nucleons so that they overlap just a little bit, then the quarks might be close enough together that they're free and they're not bound to any other quark. If we can do this experimentally, then we might make a quark-gluon plasma, a little piece of the early universe in the lab. One way we could do this is to start with two nuclei and accelerate them to very high energies and let them slam into each other. And this is an anatomy of a relativistic heavy ion collision. So you start on the left with two nuclei and you accelerate them to very high energies and they come slamming towards each other. Now the reason they look like pancakes is because special relativity says that if something's moving near the speed of light, it's going to get shortened in the direction of motion, so they'll just look like these pancakes. The collision causes the nucleus to heat up, and eventually you get this hot, dense system that is the quark-gluon plasma, but because we can't contain this in any way, it just continues to expand and cool, goes through a process of turning back into hadrons, into the normal matter that we see, and then these all go streaming out. And that's really the process. So we have a model of how we might proceed to make this quark-gluon plasma, and we have an idea of what it might look like. So it's, again, it's kind of like a miniature Big Bang. So we can actually do this with an accelerator, particle accelerator, that's called the Relativistic Heavy Ion Collider at, or it's called RHIC for short. It's at the Brookhaven National Lab on Long Island. It spins beams of atomic nuclei up to a speed of about 99.95% of the speed of light, so very, very fast indeed. It's got rings that point in opposite directions, so you can spin them up and get them going to their highest energy and then let them cross and slam into each other. Each ring is 2.4 miles around. And I want to say something about the size of this because I'm often asked, why do you need a certain size of accelerator? And the higher an energy you want to go to, the larger an accelerator you need. This is for a number of technical reasons, but just know that looking to shorter distances means a larger accelerator. Going to high energies means a larger accelerator. So this is the accelerator that I've been using for my work for the past 10 years. The beams are allowed to cross at certain specific locations, and that's where we can look for these collisions. And keep in mind that model of the collision with the two pancakes moving towards each other. Now we have to devise a way to look for evidence of the plasma formation. This is getting into tricky territory because there's no way to confine it, and so it only lasts about 10 to the minus 23rd seconds. And David and I were discussing, do we have any way to visualize 10 to the minus 23rd seconds? And honestly, I couldn't think of any. But it's not important because what you need to know is that this doesn't live, this lives such a short time that we couldn't possibly see it directly. So what happens is it expands and it cools. And when it cools, it turns back into normal matter. And this is a picture of the time evolution of a collision. It's very cartoon-like. Along the right-hand side, you can see the stages of the collision that are similar to what was on the other slide. And you start with the protons and neutrons at the top that were in the nucleus, and then something happens, some process happens by which they this overlap takes place and they become this quark-gluon plasma. And then as it cools, it turns back into normal matter, and then this normal matter can stream out into your detector, and you can observe that. It's very much like if you've got steam coming out of a kettle. The steam is made up of invisible water droplets, and then it expands and it cools, and as it cools, it begins to turn back into water, and that's what you see as the cloud of white around the steam. So what we're going to do is try to infer what happened during the collision by studying the properties of these ashes of the quark-gluon plasma, the normal matter. So all of this takes place in a realm that is far removed from our senses, as you might imagine. So we have to build a detector that can tell us about the particles that are streaming away from the collision. At RIC Energies, we commonly use gold nuclei for the beams. There are 197 nucleons in each gold nucleus for a total of 394 particles going into this collision, half from one side, half from the other. But because energy and mass are equivalent, Einstein told us that, E equals mc squared. You have to say that in any physics talk. The energy that the accelerator gives to the gold nucleus, that energy gets transformed into mass. So that in fact what you get streaming out can be 4,000 or 5,000 particles that are streaming away from where this single collision took place. So this is a real experimental challenge, both in detecting and identifying some or all of these particles, and in simply managing the vast amounts of data from the experiment. So my detector is called Phoenix. This is the Phoenix detector. It consists of 4 arms pointing out at 90 degrees each with a large magnet and then many layers of detectors. So you can see the 2 arms on the top, that round thing in the middle is a magnet, and these are layers and layers of different types of detectors. We can identify a charged particle by observing how it bends in the magnetic field, and we can identify neutral particles by detecting the energy that they deposit in other detectors. The central arms detect hadrons, electrons, and photons, and then the arms below detect muons. These are a kind of heavy electron. The red arrow off to the right shows the height of a person relative to this detector. So it's a very large detector. The detector has to be large because if you've got 4,000 or 5,000 particles streaming out of the collision, they have to separate far enough so that we can track them individually. And if they're all close together, it'll just look like a wash. So we need to have a big detector to see each individual track. And it has to be very complex because we have all these different types of particles we want to identify, and each one has a different way of identifying it, and so we need to have that complexity and that size. So, and I want to talk just for a moment about what it's like to build a detector like this, not from a technical standpoint, but what does the process look like to the people who are involved? The path from idea to completed detector is long and about as complicated as the detector itself. As soon as it's known that a new detector will be built, people get very interested, or a new accelerator will be built, people get very interested in building the detectors that are the eyes that the experimentalists use to see into the submicroscopic realm. So small groups will form around ideas about the interesting signals, which determines how the detectors should look and operate. Meetings are held, reports are written, and the groups get larger. Soon it's time to apply for funding. Usually there's only space and money for a few ideas. This is where it gets tense and rivalries intensify. In the case of RIC, there were 4 groups with widely different concepts about what would be the best probes to use to detect the quark-gluon plasma. One was funded, but the other 3 were not. Instead, they were told to go away, work out the differences, and come back with plans for a single detector. Think of it as a very high-tech arranged marriage, and you will have the Phoenix detector. So out of the ashes of the 3 failed projects, Phoenix was born. We were really lucky because we managed to combine the strong parts of each idea into something that we could get enthusiastic about. It doesn't always work like that because people actually get emotional about these things, and sometimes you just end up with all the worst ideas in a detector, and it doesn't work. Once we have the concept and the funding, it's time to get started with the actual building. However, a detector like Phoenix is too big and too complex for even a few groups to build. So you have to sell your physics vision and you have to sell your detector idea, which are intimately connected, to several groups. And once you have enough groups, you divide up all of the work and say, I'm going to build this one, I'm going to build this one, I'm going to build that layer. So each of you is going to build a different layer of this incredibly complicated device that's still pretty much a dream. And each group agrees to design and build part of it. So you're told, well, it's got to fit in here, and it's got to interface to the rest of the experiment like so. But other than that, you go and you work out the details and just make it do what it's supposed to do. In my case, because I was involved in building part of Phoenix, this involved flying to Italy to get giant circuit boards from a particular manufacturer, many visits to Oak Ridge to make sure my electronics were designed and built, trips to Israel and Sweden to check on smaller detectors and readout cards that were being built, and endless, countless meetings. Will it all still fit together when we get all the centimeters converted to inches and back again? Somewhere in the middle of all this, the experiment runs short of money and has to cut back. By now, everyone is so involved with their individual detectors that you might as well ask them to amputate a limb. But we have more meetings and we move on. Eventually, it all shows up, and by now you have hundreds of people, but everyone is still working endless days and long nights because you don't want to be the one on the critical path, the one whose detector isn't there. And there aren't so many fights now because most of the decisions have been made, for better or for worse. And physicists aren't so much into recriminations as into actually making things work. The graduate students are running cables everywhere. The postdocs are hooking oscilloscopes up to all the tender parts of the detector and forcing them to life. The young research scientists are thinking ahead, what is the next problem I'm going to face? What is the next step? And they're all looking to the senior scientist who came into the room, and they're just hoping, please, that he doesn't touch anything. So gradually the detector comes to life, first with cosmic rays and then inside the accelerator itself. And all of these people are learning how to make it work. It's the most complex scientific device ever built, at least for a few years, with hundreds of thousands of channels of electronics. It weighs 3,000 tons and is as big as a house. And it will spit out petabytes of data. A petabyte is 1 quadrillion bytes. It needs every one of the hundreds of people, 69 institutions, and 14 countries that built it. And it will work spectacularly well. So the temperature inside the collision can reach about 10,000 times the temperature of the sun before it starts to cool and hadronize. So this is very, very hot. Once we have recorded all of the signals from the detectors, we use complex pattern recognition software, which we all have to write from scratch, to determine the tracks of the charged particles and where the neutral particles hit. Here we see a display of all the tracks from a single collision going into the two arms of the central tracking arms of Phoenix. So you can see the basic two-arm structure that we saw on the mock-up of the detector. I can also show a picture of me with my experiment that my daughter drew when she was little and was supposed to draw her mother at work. And this is her concept. It looks like a plant. I don't know what the thing on my head is, but I was so excited that I could recognize the detector. So once we know what particles came out of the collision, how fast they were going, and what direction they went in, now the real work starts, because you have to start thinking very, very hard. That is to use this information to try to understand what happened during the early undetectable stage of the collision. You know, we're sifting through the ashes. The process by which the hundreds of physicists organize themselves to analyze and interpret the data, agree on the results, and write and publish the scientific papers is a story in itself, and I don't have time to talk about it at the moment. But it's sufficient to say that complexity breeds necessity, and too many cooks do not spoil this broth, but make for some very solid science. But now we need to find signatures that tell us whether we have found the plasma. On Phoenix, we use a lot of complementary measurements, enough to fill up hours and hours of talks. But I'm going to just describe a couple of them. So one thing we can do is to look, this is just another kind of a model of the collision where you can see the two nuclei going past each other, and this hot, dense matter that's formed is left behind, and it's expanding and it's cooling. And we can watch what is the pattern of the flow of this matter as it comes out of the collision system. The flow pattern is going to depend on a number of things. It's going to depend on how strongly the matter is interacting. It's going to depend on how soon it reaches thermal equilibrium. Then we can try to describe the flow using different models and say, well, we put this into a model. Do the data look like this, or do they look like that? So I'm going to show you a plot of data. There's only 2 plots, so. And what we have here is a measurement on the vertical axis of how the matter flows out of the collision. And each strip of data, each different strip corresponds to how head-on the collision was. Because with a gold nucleus, they could hit head-on, which is going to put a lot of energy into the collision, or they could just graze each other and put less energy into the collision. So first of all, the top one is the most head-on collision, and then the bottom one is the least head-on collision. So the first thing you see is that you get the most particles coming out of the most head-on collision. The most matter just comes out of the most head-on collisions, which is very much what you would expect. And then the solid lines are the model calculations. So we find for this particular model so this model is called hydrodynamics, and this is, as the name implies, a model that describes the flow of fluid or the flow of water. We find that there's really good agreement, at least out to I should mention that along the bottom, what that is just a measure of the momentum transverse to where the collision took place. So it's kind of what's going out, how far out to the side something's going. And you can see that this model, hydrodynamic model, fits the data very, very well. This was, and the input to this is that it's a fluid with a 0 viscosity, which we call an ideal fluid. An ideal fluid has 0 viscosity or 0 resistance to shear stress. So nature rewarded us with a real surprise, because we had not expected this at all. We had expected this was going to look like some sort of a gas. And the fact that it's, in fact, a liquid was really a fun and novel, unexpected result. Okay? So another thing we wanted to look at was whether we see evidence for quark degrees of freedom. And what that means, if you could imagine something made out of the nucleons, well, everything can go in 3 spatial dimensions. And so there's only so many ways that the system can move when you've got just the nucleons. But if you've got a system where the quarks can move around freely, all of a sudden you've got many more different ways the system can move, because the quarks can move freely in that system. And so we can try to observe this. So we have a way to quantify the direction of the flowing material. It's formally called the second Fourier coefficient of the expansion in momentum space, but we just call it either elliptic flow or V2. And just think about it as the more asymmetry in the distribution of the matter flowing out of the collision, the more V2. Okay? And here's a plot of V2. So first we plot the V2 for several different types of particles. We can see that each type of particle follows its own distinct curve. And if we divide, so that's the one on the left. So these are different particles. There's each color corresponds to a different particle, and this is the V2 of each of those, and they all look different. But if you divide by the number of quarks, which is the NQ on the right-hand plot, what you see is that they all look exactly the same. And what this is telling you is that this system is really acting according to the number of quarks in the system. It's the quark degrees of freedom that are determining what happens. So we are, in fact, seeing evidence for those free quarks. Okay? So we must have produced a system in which the quarks were not bound into the hadrons, which is exactly what we were trying to do. So this is evidence from the Phoenix detector for the fact that we have produced this deconfined quark-gluon state. So here's the cover story from the issue of Scientific American describing the discovery of the quark soup. This was very exciting. And here's a shot of the CNN coverage after our announcement. And it says, the early universe didn't blow so much as flow. New results from a particle collider suggested that the universe behaved like a liquid in its earliest moments, not the fiery gas that was thought to have pervaded the first microseconds of existence. So this was something really new. Of course, it isn't just enough to have cooked up this primordial broth, and now we have to savor it. For scientists, this means more experiments to understand how it's made, what it's like, and what are the broader implications for our understanding of the universe. And we will push out to a new energy frontier. The Large Hadron Collider, a new accelerator currently being commissioned at CERN, is capable of accelerating heavy ions, as well as the protons that were the main purpose for its construction. It is 17 miles around. Collisions between ions will have about 30 times the energy of RIC, and the matter produced will be hotter, bigger, denser, and longer lived. The detectors are much larger, more complex, and it takes thousands, not hundreds, of physicists to build and operate it and to understand the results. It'll be quite a banquet. Thank you.
Thank you very much, Vicky. We're going to start off, I'll just ask her a couple of friendly questions before we open it up to the hostile audience. I guess I've got a really simple question to start with. It goes like this. If you were looking at traffic patterns in the Nashville area, you wouldn't just study collisions. You'd look at the way that cars were going around not hitting each other. And I'm just wondering why physicists are so, focusing on when these particles hit each other. And I mean, why not just let them not hit each other and see what they were doing when they weren't interfering with one another? Well, what's the collision thing? What is that all about? I know it's a pretty simple question.
No, it's a great question. So is this on? Okay. Okay, it seems to be. Okay, well, first of all, you have to produce the particles on their own. So some of these particles are not, you don't just find protons around, they're bound into a nucleus. So the collisions let you make the particles in the first place. Then if you want to study how they interact, you have to make them where you want them to be. So you have to build an accelerator and have the collisions take place where your detector is. These particles, the one place you do see particles streaming down, and you could watch them interact, just let them interact and not do the collisions, is the cosmic rays. Their cosmic rays are streaming all the time through everywhere. And you could, and a lot of, before we had accelerators, what we did is we would build a very large detector and just let it sit there and look at the sky. And along would come the particles. But they don't come along very often. And when they do come along, they might or might not hit your detector. So it would take an incredible, a long, long time to actually collect enough data to really understand what's going on. So the collisions just let us produce the particles instead of waiting for heaven.
Okay. Well, here's my next question. You're recreating the conditions some very short time after the Big Bang. I mean, one of the questions I have is, well, recreate it now? I mean, can't there be parts of the universe where this stuff's happening again or still? And if that's not the case, I mean, if these are sort of conditions that happened once and will never be repeated, what is the point of finding this out for trying to understand the universe as it is now? In other words, I'm trying to say, if that just happened once and we can artificially recreate it in this lab situation, surely that tells us something about what happened a very long time ago, but it doesn't tell us anything about the way the universe is operating now. Or why couldn't the universe itself be constantly creating things of the same order as the Big Bang? I mean, why should it just happen once? Could it not? Is that a fair question?
That's two questions rolled in together.
I was trying to get, double.
Yeah, you're double dipping there. First of all, the question of does this happen, why can't this happen in our universe? In a way, the way we define our universe is bounded by what we can observe. And we do not observe other universes. I don't know that another universe would connect to ours in any way that would make observation possible. So, so I'd say that almost is a question that doesn't quite make sense.
No one's ever said that to me before.
I said almost, yeah. So the other question is, what was the other question there?
The other question is, well, so now we know what happened,
Oh, why do we do this?
Yeah, why do we do this?
Well,
That's history, isn't it?
no. One thing that we believe is that, and so far this seems to be true, that what is constant in the universe is the fundamental forces and the basic particles. This is not something that changes in time. So the way the fundamental forces were in the early universe is the same as the way they are now. The force that I spoke about, this color force or strong force, it's a tricky thing to work with because there is a theory that seems to be correct, but is very hard to do calculations with. And some of the implications for this theory are not very well understood. So the major motivation for us doing this experiment is to understand the strong force better, more so than trying to understand the Big Bang. I simply chose to focus on understanding the Big Bang better, but our knowledge of the strong force as it was in the Big Bang is every bit as relevant today as it was then.
Okay, just one last completely kind of off-the-wall kind of question. As a scientist, if you're talking about the creation of the universe, and as an educator, how do you respond to someone who thinks that the universe was created, let's say 6,000 years ago, by God, directly? How do you, because I'm looking at your presentation, and it's beautiful and impressive and believable, and yet there are obviously people for whom this whole story is just a fiction made up to blind us to the truth. I just wonder how you would deal with someone who contested everything you were saying.
It depends on what kind of conversation someone wants to have. If they're interested in learning the scientific evidence for the Big Bang, then I would talk about the motion of the stars and the redshift and how things that are further away have a larger redshift, a higher velocity. And so that suggests that everything was at a point at some time in the past. On a really good day, I could talk a little bit about evolution and give some evidence for that. So if they want to have that kind of conversation, then that's what I would say. If they wanted to have a conversation in which they challenge the validity of the science, then I think I could simply argue why this is correct in terms of the evidence that's presented. If they want to have a religious argument, I think at that point I would just say, you know, I have my beliefs and you have yours, and I'm probably not going to be able to convince you.
Okay. Well, we're going to take some questions now, and this time we're just going to have one question at a time and see how that format works instead of having a collective bunch together. So, don't spend too long.
Okay.
Well, all I have to say is, gee whiz, I wish I paid more attention to physics when I was in school. This is incredible. As a scientist, this has to be really neat. It is high gee whiz factor, but as an audience member, I'm sitting here saying, gosh, a lot of money has been spent on this. It does begin to answer some of those questions when we were all 12 years old and sat on a blanket on a sunny, you know, or a summer evening and looked up and said, gee, how did all this happen? So that's fascinating, and I salute you for it. But I also wonder applicability, whether it's in your generation or whether it's you 3 generations down that takes your learning and maybe applies it to something in the future. I mean, you have to have that feeling. And with that thought, what inspires you for future generations or even this generation to take that learning, and what also scares the bejeebers out of you? What could this lead to? Thank you.
That's, again, a lot of questions. As far as applicability goes, I think about the fact that the World Wide Web was developed at CERN as a way for scientists to communicate with each other. It wasn't planned to turn into what it's turned into now, but it certainly happened. And right now, one thing that's being developed as a consequence of these experiments in order to just handle these vast amounts of data is the grid and the interaction of a lot of computer systems to do processing. And this is something that's being developed in this context. So there are practical things that come out of it. What motivates me is lying on a blanket looking up at the stars. That's, to me, it's very interesting. I love to talk to children about it and hear that they think it sounds really neat, and maybe some of them want to study science. What scares me? I think what scares me is ignorance.
Do you mean your ignorance or our ignorance?
The collective ignorance.
Hi, a couple of questions, maybe a different line is looking at your picture there. I was involved in trying to get the SSC placed in Tennessee. I think it was canceled around 90, something like that, which was very short-sighted thing that happened because it wasn't that much money. But I want to, is there any plans that you know of to maybe try to start something like that? I think it was going to be the largest one in the world if it was built. They started in Texas, but do we have any plans to try that again? And what's the current state of nuclear fusion? Do we have any prospects for that? Or I've been hearing about this for 40 years and so far nothing. And if so, what do you think is the best approach to achieving that?
Can you translate SSC? We don't know.
Superconducting super collider. It was a large accelerator that was going to be built and eventually sited in Waxahachie, Texas. This accelerator is 17 miles around, and the SSC was supposed to be 54 miles around. So it was enormous. It would have put us at the forefront of particle physics research probably forever. And it was canceled in just some almost random budget cutting measures that were taken. That was in 94. And So the, I've forgotten the second part of the question. I can only answer one question at a time, and then I forget. No, not cold fusion. Well, nuclear fusion, that's definitely far outside of my field, but my understanding is that no one has, as of yet, managed to even break even with fusion processes. I think right now what we're going to see is we are starting to see is the return to traditional fission reactors as a response to climate changes. And so this is something that will pick up. I'm not sure what the future is for the fusion research.
Lady up here.
I think these colliders are fascinating, but I would like to ask you to go to the very beginning of the operation, and like if you shoot a gun, a bullet comes out and it goes really fast. So how do you get the particle in there to know where it's supposed to go? How do you know that it's going to collide with the other gold one and not some odd thing that you don't know that's in there? I mean, it can't be in a container because the container would be particleized. How do you get it in there and make it go?
You start out with something, basically you boil some atoms off. We use gold atoms a lot. You boil those off and use an electric field to move them around. We go through a process of taking all of the electrons off so that we can steer them very well through electromagnetic interaction. We then send them into the ring, and again, it's all controlled by radio waves to accelerate them and magnets to bend them into a circle, and you just keep sending them around and around. Now, sometimes they do get lost and they go places you don't want them to go, and the place that you most don't want them to go is into your detector when you don't want the beam to go into your detector because they're very delicate and very close to the beam, and it can do some damage. Otherwise, all of these accelerators are just shielded with many huge blocks around them. So anything that could make it out of the accelerator will just go slamming into a big shielding block. Does that answer your question?
Close. It helps.
Besides being larger, how is CERN different from RIC?
For the purposes of the relativistic heavy ion program, we expect that the system will be larger, that we can produce. It'll be larger and it'll live longer. And it's another possibility is, I'm said in passing that the quarks, the interaction between the quarks is strong in this. It's possible that as we go to higher energies, we'll actually reach a point where the coupling is very weak, and that will be a whole new regime to study. So we don't exactly know. That's just what we think. If we knew, we wouldn't have to do it.
I'm going to go back to Dr. Wood's question, which, and I think my question will be unintentionally directed to his. You talked about the universe. There's a theory floating around now that maybe there's a multiverse, and there are dimensions that we don't know about yet, and that in fact there may be universes being created right now. What can you tell us about that?
Well, the theory that the theory that has the most credence, I would say, as far as forming multiverses goes, is that there's this question with quantum mechanics where when you make a measurement, it causes you have a system where the properties are not determined at all. The properties don't exist. Like, for instance, the size of it might not be well defined. And then you make a measurement, and you say, okay, it's right here, it's this big. And that does what we call collapse the wave function that describes that thing. Now, many of us, myself included, think that's just the end of it. You happen to collapse it down to that wave function, and now the universe goes on with that collapsed. Some people have put forward the theory that, in fact, what happens every time one of those measurements gets made, it actually splits the universe into all the possible paths that it could have been taken. Could be here, could be there, could be there, and you now have 3 universes, one in which it's in each of those things, and every single measurement forms a different path, and these are just multiple universes. Yeah, it's not the standard belief, but it's not contradicted.
So what I don't get about that is where would all the energy and matter come from for these other universes? I mean, I understand it sort of logically, but I don't understand, where you get the funding from.
I'd probably sweep that under the rug of the uncertainty principle.
May I ask one here? I saw a number of artist renderings, drawings of shapes and sizes, and I'm wondering, mass collides with mass, energy is formed, particles result. Are you able actually to see those even with the most high-tech electron microscope or not?
The best resolution right now is at the atomic level. So you would not be able to see these particles. You wouldn't be able to resolve these with that type of a microscope.
Can you describe a singularity?
I can say the words. It's in the context of this talk, we believe that a singularity existed at the beginning of the universe, and what that means is that all of the matter in this object is collected at a single point. It has no extent to it. It's just collapsed down into a point. So it could be very massive, but have no physical dimension. Well, it would have actually, you wouldn't be able to measure its physical size, but you would definitely feel the effect because it would be like a black hole. A black hole is a singularity, and you've got a lot of mass collapsed down into a very small point, which would make a hugely strong gravitational field, and you would feel that field. There would be enormous tidal forces. Light could be sucked into that field. So you would definitely know that it was there, but what the size was, you wouldn't be able to figure out.
And the entire universe is concentrated in that small singularity.
Yes, that's the theory.
I think that may have to be the last question.
So if I understand this correctly, time has gone in infinity both directions, after singularity and before singularity. What I'm asking is, our universe was formed as singularity, but there was energy and mass before that. Something came together that existed, in infinity going out the other direction. Just singularity, our universe, matter that was created, was formed. Everything didn't start at singularity. There was a whole existence of matter and or force before singularity. It just wasn't in the form of our universe. Is that correct?
Right now, we're struggling with trying to measure these ashes of this quark-gluon plasma transition, and that's 3 microseconds after the Big Bang. Now that may sound like not very much time, but on the scale of what happened in those 3 microseconds, that is a huge amount of time. We don't really have any observational or experimental handles on what happened before that, because right now we think it's not possible because it was so hot and so dense that it just obliterated any evidence for what went on before. So if we can't gather evidence for it, then it's very hard to think about turning it into a meaningful scientific question, which is all about evidence.
I think it's time we thank our speaker and come back again.